Okay, this is a video that should demonstrate the repulsion of two wires when they have currents flowing in opposite directions. Here's the source of the current, and what I'll do, I'll adjust the current by doing that. So I'll increase the current and then I'll decrease it. And what I have is I have the current flowing through these two cables here, going through two enameled wires. And it's basically going all the way to here. And the wires are connected here, and so in one of these cables, in one of these enameled wires, current's going in one direction, and the other it's going the other direction. So current's going in two opposite directions. I'm going to turn on the current and turn it off, and we'll see what happens to the separation between the two wires. See them going further apart? Turn it off. Turn it on. Turn it off. Turn it on, turn it off. Okay, so that's the repulsion of two wires when current's flowing in opposite directions. Now we'll make the current flow in the same direction on the next segment. Okay, in this case I have the current from one of the clips going through both wires here, and then coming out at the other side there. Let's see if the wires tend to attract each other when I turn it on. They at least seem to demonstrate that when the current is flowing in the same direction. See the space getting narrower between them. Alright, so you've seen both the repulsion and the attraction. Now we'll talk about it. Alright, for this thought experiment, to help explain what forces the wires are experiencing, imagine we have a blue wire with current flowing upward. So what is going to be the magnetic field generated by this blue wire and its current? Well, I'm going to put my thumb in the direction of the current and then wrap my fingers around the wire. So on this side of the figure, my fingers are going to be pointed into the page, and on this side, they're going to be pointed out of the page. So I'm going to draw my X's and O's to reflect that. So when they're into the page, I have blue X's that I'm going to put here. Where they're out of the page, I have blue dots. All right? And I can extend this further because the magnetic field exists further away from the wire too. I can do this. It's going to be weaker, so I'll draw fewer of the blue X's, and I'll draw fewer of the blue dots out here. But the overall picture is going to look something like that. Now near that wire, I'm going to put another wire going with current flowing in the opposite direction. That's my red wire. All right, so the current in the red wire is flowing in the opposite direction, just like I did in a little demonstration. I'm going to do the same thing. I'm going to put my thumb in the direction that the current is flowing, wrap my fingers around the wire, and draw the corresponding magnetic field lines in terms of whether they're coming into or out of the page as a result of the red wire. So on this side of the red wire, the magnetic field, remember the magnetic field does donuts around each wire. And the question is, what's the direction in which the magnetic field line should be drawn? And it's the direction that my fingers are. So on this side, my fingers are pointed into the board. So I'm going to draw red X's here. And I'll draw a couple here because they also exist further away from the wire. And on the other side, I have red dots, because this is where the magnetic field is coming out of the board. All right? So now what we're interested in is, how is the blue wire affected by the magnetic field created by the red wire? And how is the red wire affected by the magnetic field created by the blue wire? That's going to determine what force the wire feels and what direction that force is going to be. Well, I'll show you how to calculate it in a few minutes, but I want to show you first the direction of the force. So let's look at this. The current flowing up means the charge is flowing up into the wire, upward in the wire. So I push my fingers that way, but that's taking place in the presence of red magnetic fields directed into the board here, or into the page. So what I got to do is I got to push my fingers up that way, bend them down, and what we're going to see is that when I bend them down, okay, so let me repeat where I was at. Put my fingers in the direction of the current, bend them down, my thumb points away. So the red wire is going to experience the force this way. The blue wire is going to experience the force that way. You're going to experience a repulsion between the two wires when current is flowing through them in opposite directions. Now I'm going to repeat this and have the current flow through the wires in the same direction. Okay, my first step in thinking about this is to wrap my fingers on the wire when my thumb is pointed in the direction of the current. And in both wires, it's going to be up. So point my thumb up, draw the magnetic fields associated with the current that's flowing through the wire. So this blue wire is going to create the magnetic fields that are coming out on this side and that are going into the page on this side. And they're also going to be coming into the page or all the way over to here. The red wire, on the other hand, is going to, well, it's going to be the same because its current is flowing up. So on the left of it, it's going to have the dots, some of which will reach the blue wire. And on the right of it, of course, it'll have the X's, just like the blue wire. We don't really care about those right now because we're interested in the effect of the red wire on the blue wire, and the dots say it all. So let's look at what's going to happen to the blue wire. Put my fingers in the direction of the current that's flowing up. Current, remember, is the flow of charged particles. Positive charged particles is what the current represents. Bend my fingers in the direction of the magnetic field that's out of the page. My thumb points to the right. So the blue wire is going to be attracted to the red wire. Let's look at the red wire. Put my fingers in the direction of the current, which is, again, the direction of the motion of the positive charges, that's up. Bend them in the direction of the magnetic field caused by the blue wire, and the red wire is going to also feel a force that way. So this is going to be an attraction when the two currents are flowing in the same direction in the two wires. And you saw it in a demonstration, and now you see the explanation as to why. And shortly we'll actually do calculations of how big the forces can be. I thought it important to talk about one or two more problems related to homework 6 that you'll see. One of them is about a magnetic field that's pointed in a certain direction. I'm going to call it a uniform magnetic field of strength B, and a current that's passing in a wire through that magnetic field. First of all, let's think about what direction of force the wire is going to experience, because that's what happens. Matter of fact, in the cases with the two parallel wires that we just talked about, it's the magnetic field of one wire that's causing the force on the other wire. In this case, all you have is an external magnetic field, not necessarily caused by another wire. But we can use the right-hand rule. We can first put our fingers in the direction of the current. Then I'm going to have to do it upside down. This is hard to do with the camera for my right hand, but if I could put my fingers in the direction of the current and then bend them in the direction of the magnetic field, my thumb would point into the page. And that would be the direction of the force that the wire would experience. So the wire would experience a force into the page. So if I could draw the force as a black symbol, it would be X's, representing that the wire experiences a force into the page. Now the question is, how big is the force? That the wire experiences due to the current and the magnetic field. I write magnetic field B field for short often. It's a question. Well, let's think about it conceptually. The bigger the magnetic field, I'm going to write force here. The bigger the magnetic field, you can imagine, the bigger the force the wire is going to feel. If there's no magnetic field, the wire would not experience any force from the current flowing through it. So B is directly proportional to the force. The other thing that's proportional is the current. The bigger the current, the bigger the force you're going to experience, because the more charges are flowing through, they're each experiencing a force, and it all adds up. And then the other thing is the length of the wire. The longer the wire, the more force it's going to experience. So we can also write it as the force per unit length, if you like. That's another way to think about it, is equal to B times I. Or if you want to know the complete force, it's the size of the magnetic field times the current times the length of the wire. That's going to give you, believe it or not, units of newtons. Magnetic field is unit of Tesla. Tesla times a current times a meter, a Tesla amp meter is Newton. It's another one of those conversions. You can take a look at that and see. I thought I'd do an example similar to one of the homework problems. This is an example similar to a homework question. Pretty straightforward. You have a current flowing through a wire. The size of the current is 3 amps. And there's a magnetic field present, which I'm saying is 0.2 Teslas. That's this. And you know how to do the direction. We just did that a minute ago. But how do I determine the force per unit length? Well, it's simply magnetic field times I. So I multiply 3 amps times 0.2 Tesla. And I'm going to get, if you look at the units carefully, it may seem funny, but this would be also units of force per unit length is newtons per meter. So it would give me 0.6 newtons for every meter of wire. So if I have 2 meters of wire, that wire is going to experience a force of 1.2 newtons. But that's how you can determine the force per unit length, which is related to one of the homework problems you'll see. I now want to show you an example of a very practical application of charges and how they're affected by magnetic fields. In this case, it's going to be a uniform magnetic field as represented by these blue X's on the sheet. And a positive charge is being projected into this magnetic field. I'm going to say that it has an initial velocity here. I'll just give it an initial velocity of v directed to the right. And I want to think about what's going to happen to the charge when it enters the magnetic field. Well, we know, I'm going to use the right-hand rule. I know that when the charge enters, it's going to be moving to the right. I'm going to put my fingers in the direction that the charge is moving. Well, in this case, I rotated my paper, so now it's moving up, so my hand can show you on the video screen. And then the magnetic field is directed into the page, so the charge is going to experience an upward force when it enters the magnetic field. So that's what we've talked about already. So when the charge enters in here, it's going to move in here, but as soon as it moves in here, it's going to experience an upward force. Well, does that mean that it's immediately going to move and be directed upward in terms of its motion? No, it means it's going to be accelerating in the upward direction, but it's still moving to the right. So what that actually means is its motion is kind of bent. And each instant that the charge bends, its velocity is now going to be in this direction, and the magnetic field, of course, is still pointed down. So then the force is going to be not upward, but that direction. And what we're going to see happening is as the charge moves, it's going to follow a circular path. As long as there's a magnetic field there, I'm going to assume that's a uniform magnetic field wherever the charge is. That charge is going to follow a circular path. And if the magnetic field exists all the way over here, it'll just start spinning in a circle. And this is interesting because it has a real practical application, but first I want to figure out how big is the circle? What is the radius of the circle that the charge is going to trace? So what's the radius of the circular path that the charge traces? So what I want to think about is, well, how big is the force? We talked earlier that the size of the force, the bigger the charge is, the bigger the force is going to be. The faster the charge is moving, the bigger the force is going to be, and the stronger the magnetic field, the bigger the force is going to be. This is the actual calculation for the size of the force of a charge, a positive charge, moving with a speed v through a magnetic field b, assuming that v and b are at right angles to each other. This is how big the force is going to be. All right? That force is the force that's causing the charge to stay in the center of that, or to follow a circular path. And if you remember from Physics 1, when an object follows a circular path, there has to be some force that's causing it to follow that circular path. That force is called a centripetal force. And what's going to actually happen is the charge's speed isn't going to change. Its direction is going to keep changing, but its speed's going to stay the same. So I can actually say that I can apply Newton's second law, which we did way back in first semester physics, and can say, okay, the force that the charge experiences is equal to qvb, but it's also equal to mass times the charge's acceleration. And because it's moving in a circular path, that's a centripetal acceleration, which is v squared over r. where r is the radius of the circle. So I'm going to rewrite this on the next page. I'm going to substitute for force equals qvb, but force also equals mv squared over r. So I'm going to equate qvb and mv squared over r, and let's see what we get. qvb equals mv squared over r. All right, so that's the path the charge follows. And this relates the radius of the path and the speed of the charge and the strength of the magnetic field. Let me solve for r, and we'll actually see that one of these v's is going to cancel. You can cancel it with red. All right, so what I'm going to get is q times b equals mv over r. And I can find the radius of the path that the charge follows, multiply both sides by r, divide by qb, and I'm going to get that r equals mv over qb. So let's think about this conceptually. The bigger the mass particle is that the charge is sitting on, the harder it is to turn it, so it's going to make a bigger radius. The faster it's moving, the bigger a circle it's going to trace as it's accelerating as a result of the force it experiences. So m and v, when those are bigger, they make the radius bigger. But a bigger charge is going to have a smaller radius because it's going to experience more force causing it to bend, and a stronger magnetic field will do the same. It'll cause the charge's path to bend. So this equation kind of makes sense, and it tells us what size radius the charge is going to follow when it goes through that path that we drew over here. That radius is given like that. So in other words, a big charge, if the charge were bigger, 2q, let's say, then it would be a tighter curve. If the charge had more mass, if there's more mass on this charge, so if it was a big object but the same amount of charge, it would have a bigger radius. So what this actually allows us to do is it allows us to we can put collectors that can count the amount of material coming in at different points along the path that the charge follows. And from that, we can figure out this. For instance, if we know how big a charge is, we could figure out what its mass is as it's coming out of here. So it's a way we can categorize material going into a region. If we're not sure what it consists of, we can accelerate it through and push it into a magnetic field, and then cause it to separate. And that separation allows us to determine characteristics of the matter and what comprises it. And many of you will recognize this. This is a mass spectrometer. You may have used it in a different class. This is how it works. It's the basic physics that allows us to separate the particles based on their charge and on their mass. The only other thing I want to say about the mass spectrometer is in order to get the charge to move at the right speed, what you have to do is you have to accelerate the charge. So you can accelerate the charge. And how would you accelerate a charge? This is kind of a review. It's going to be on material on exam 3, which I will do a review session for. But if you put a charge in an electric field, that electric field will cause the charge to accelerate. And then you can have the magnetic field like we just had earlier, and you'll have these fast-moving charged particles entering the magnetic field as a result of them being accelerated by an electric field. All right, so the electric field, of course, is going to accelerate the charge in the direction of the electric field. That's by definition. Electric fields cause positive charges to move that way, and negative charges, of course, to move the opposite direction. But this method will cause a charge to accelerate, then enter a magnetic field, and then follow a certain radius depending upon the size of the charge and upon the mass of the particle. And from that, we can identify what the different constituents are of a sample. Again, the mass spectrometer. All right, I'll remind you more about how electric fields can cause charges to accelerate in a review lecture. The very last thing I do want to say, though, is that the total force that a charge can experience is the sum total of the force it can experience from being an electric field, Q times E, plus the force it can experience by being in a magnetic field, which of course is at right angles to both the speed of the charge and the magnetic field. So these are the two things that can result in a force on a charged particle. And you'll see this in the PowerPoint slides too. This is often known as the Lorentz equation. Okay, and I will talk to you shortly in a review video.